You see this? I don't know.
So Zakadis, are you still here?
No, I interrupt.
No, he's the one sharing.
Okay.
He's sharing it.
How do I do now?
He doesn't know to do it.
No, I don't understand why Professor Zakadis is still.
No, he's his own.
Oh, okay.
This is mine.
Remove the cord.
This is mine.
Yes, remove the cord.
You have to remove the cord.
He's making call.
You can start.
The same as yesterday. Okay. Anyway, I begin the lecture. In the lecture yesterday, I have shown some examples, in particular binary random variables, one dimension and two dimensions. Now we come to beyond examples to say random variable with arbitrary distribution. Of course, we assume our movement, existence of our movements. Okay. First of all, we see only one random variable. This I taken material from the work of Arcadi and Boshev to give the random quantum decomposition of one random variables. Random variables, or let's say the distribution has all the finite moments is determined by the Jacobi coefficient. And you have two families of Jacobi coefficient. Use this, you can construct a certain Fock space to do the quantum decomposition in terms of creation, annihilation, and preserving operator. In short, we can call it Kappa operators. Use the standard notion A delta, A minus, and A z to indicate the creation, annihilation, and preserving operator. What is one model interacting Fock space? This is a typical model to present a quantum decomposition of one probability distribution. Okay. Roughly speaking, one interacting Fock space is a Fock space over C. Usually Fock space over a certain Higgs space. Now this Higgs space is just a C, very simple. Then you do the break sum of a sequence Hn. Now what is the Hn? For each n as a vector space, this Hn always is C. What changed according different n is inner product or scalar product defined on this vector space C. What's scalar product? Scalar product for each n and two elements in C, so two numbers. N's scalar product is the standard scalar product on C multiply omega 1 and product omega 1 and omega 2 and so on up to omega n. This is a scalar product on nth space. Okay. Now you have a sequence of Hilbert space, then you do the break sum and you get a pre-Hilbert space. Then this pre-Higgs space is used to do the quantum decomposition for from this definition, you see immediately in the construction of this space, we use only the family omega. Alpha is not used to construct this space. In fact, alpha is used to define the operator in them. Okay. Now, let's see some definitions of create, antedator, and preserving operators. Okay. And now on each Hn, let's return. Each Hn as vector space is just C. Of course, in C there's a very important number, number 1. Okay. And on nth space, number 1, we use this notation, phi with index n. This means number 1 viewed as an element of nth space. Okay. Now you see that in this case, you remember this is number 1, this is number 1. You see this definition of scalar product. X number 1, Y is number 1, just this product of omega index from 1 to n. As an intellectual of Roger Cardiff has used this let's say standard notations many people use. Okay. And now let's see operators, how to define the creators, antedator, and the preserving operators. I use these short notations to see these operators. First of all, A data creators is defined for each n, bring free n, the number 1 in n space to the number 1 in n plus 1 space. This is the definition of creator. And the definition of antedator is defined as adjoint, a conjugate of creator. Then in this model, very simple model, you can calculate easily. It's defined as a conjugate of this creator. You calculate easily. It brings number 1 in n plus 1 space to number 1 in n space multiply omega n plus 1. Also, this operator antedator A minus bring the free zero. One can call free zero as y human. Okay, bring one to 0. This definition creator and antedator. Preserving operator one defined as that way. Bring phi n to phi n multiply alpha n. You remember in the construction of space, we use only family omega, but family alpha now is used in the definition of preserving operator. You can see easily this space practically is isomorphic to standard L2 space. And the scalar product, each element of this, you can imagine element of this space as, let's say, a vector of infinite dimension of vectors. So, two elements in that space, the scalar product is defined as 0 space, and for each nth space, then you sum of that. This is a typical definition of scalar product of a direct sum. Okay. So we have these creator, antedator, and preserving operators. And in this respect to the base, what is base? This phi n we have no, now it's wrong. It's orthogonal but not normal base. with respect to this orthogonal base, you can have a matrix representation of this creator and preserving operator. Practically, all these three operators can be represented as matrix, a very particular matrix. First, A0 can be represented as a diagonal matrix. Diagonal elements are just that alpha k. Okay. And A plus and A minus are represented as matrix. A plus is that line after diagonal, no, below diagonal. A minus is that line after diagonal. Okay. And the element of that the matrix of A plus, the matrix representation is below the diagonal line. All elements are 1. And A minus, the upper diagonal line, all the elements are omega k for each k from 1. Okay. Now this is a very simple picture to give a quantum decomposition of one random variables equivalent to the distribution of that random variables. Of course, we need a condition that this random variables has all orders of movement. Okay. Now we see more random variables. Then, if you want to see more random variables, okay, this part I do not come to any detail. I just show you the main idea, how to construct a quantum decomposition, a certain Fock space as a quantum decomposition of some random variables. These random variables are assumed independent. This independence, I want to say classical independence. Then in next lecture, from next lecture, I show how to construct quantum decomposition by using Fock space of many random variables with some algebraic independence. Okay. Now we show, at first step, we show this construction of quantum decomposition by using Fock space, by considering the case of random variable are classical independence. As I said, I do not come to any detail. Also, one part of the material I use here from the lecture of Lucia Cardi, I understand that he will explain the standard Gaussian Fock space. Okay, so many things one can understand from that Gaussian Fock space. Practically, now we use the Fock space as a modification of standard Gaussian Fock space. Let's see. We consider a family of measures. They always assume that all the movement, all the movement are finite. Okay. Now for each k, we have a measure, and this measure associate a family of Jacobian. I add another assumption. I consider symmetric case. In fact, asymmetric case, as an idea, almost the same. The idea does not change a lot, but technically only one family of Jacobi coefficient. That family alpha and all alpha are equal to 7. Okay. Now for each measure we have Jacobi coefficient omega with index I from 1 to infinity. Okay. Now in classical case, what means independence? In practically here I do not use the definition of classical independence. In fact, I use this factorization of mixed movement. Okay. In my lecture, I say independence means a certain rule to do factorization of mixed movement. In classical case, it means this equality. And what I have now. Now for each k, I have a new k, a certain probability measure. And I can show you for each measure we have a quantum decomposition by use one mod interacting Fock space, means the Fock space over C. And this omega, in the definition of this one mod Fock space, this omega are used to define the new scalar product. Okay. And for each k we have this one mod Fock space. Because we ask classical independence, we know that classical independence in terms of means tensor product. Okay. So it is very natural to think the quantum decomposition of a sequence of probability measure, ask classical independence. One can do the quantum decomposition by taking tensor product. Okay. Now we see what should be this tensor product. This tensor product, we recall that because this at Higgs space is one dimension. At one dimensional case, the tensor product of n-fold tensor product, symmetric tensor product for n-fold, all the same, equal to that same. Okay, because it is one dimensional. And due to this factor, so this one as a vector space. This first we have a vector space means direct sum of C, direct sum of C. Then we introduce a new scalar product. As vector space, just a direct sum of C. Okay, now remember this factor. As a vector space, one mod interacting Fock space is just a direct sum of C. So this and for each C and C n-fold of symmetric tensor product of C are the same. So these two spaces practically are the same. Okay. And in fact, each nth space of this one mod scalar product, one mod interacting Fock space is equal to nth space of this symmetric Fock space over C. Okay, each of this equal to this symmetric Fock space. Take the tensor product also the same. Okay, on the other hand, we see what is this tensor product. We know general result. I guess said in the lecture of Luigi Arcadia about standard Boson-Fock space, he will give this explanation. Okay, what? If we consider the sequence of vector space and start from this vector space, we construct for each n the symmetric tensor scalar product. Then we make a direct sum, so we get the standard symmetrical Fock space. Then we take the tensor product for all k, for all index k. A result about the standard Boson-Fock space is this tensor product of symmetrical Fock space over a certain Higgs space, isomorphic Boson-Fock space of direct sum. Okay, and we use this result on our case. We have this C is like this general case HK, so this one use this these two spaces are isomorphic, and so you have that this tensor product equal to this tensor product of symmetric Boson-Fock space over C, and isomorphic to the Fock space of the direct sum. So, and imagine this direct sum gives you a vector space comparably dimensional. Okay. This gives you an idea what type of Fock space you used to give a quantum computation of a sequence of random variables, and these random variables are classical independent. The answer is to use a multiplication of standard Boson-Fock space. Multiplication, what I want to say, to define the vector space is just a standard symmetrical Fock space over a certain edge, and we can imagine as this direct sum. Okay, and this is vector space. When you need a scalar product, of course, even in one dimensional case, one mod in quantum Fock space, I can show you that scalar product very dependent on this object. If you want to do the quantum computation, now you can imagine that for this sequence of random variable equivalently, for sequence of distributions, nth scalar product, you must introduce a new scalar product. This new scalar product depends on this family of Jacobi coefficient. Algebraic structure is standard Boson-Fock space, and to do the quantum decomposition, you need introduce carefully on each nth space a new scalar product. Repeat anyway. In the level of algebraic vector space, we have just standard symmetric Fock space, or equivalent to Boson-Fock space. Okay. Now we have a picture, just a picture, and here there is not any technical treatment. Just a picture how to do the quantum decomposition of a sequence of classical, a sequence of independent random variables. This independent and classical independence. Then a natural question you can ask yourself, if instead of classical independence, I consider other type of independence, namely some type of algebraic independence, what do I do to give quantum decomposition of a sequence of a distribution by assume some algebraic independence. Okay, now I can show you the next. Okay, how do I do this?
Press down.
I show how I come to R5. How do I do? Now okay or not?
You can just press your cursor down. Yeah,
Okay. Let's see the chart 2. Is what I have said. Use a certain Fock space. Up to now, still not clear what Fock space I must use. Okay. Anyway, we can show you. I can show you what type of Fock space. Use a certain type of Fock space to give one composition of a sequence of distribution by assume some algebraic independence. Then different type of algebraic independence, case by case, I will give you definition. Okay. We start to see this problem. We start from very simple case, classical case. Okay. If we consider a sequence of distributions, I think sequence purpose, and it includes the case of n is a certain natural number. It means a finite or a sequence. Okay. Then assume that this distribution of random variables is K. And we assume that these random variables are independent, classical independence, and satisfy with the distribution of K is just this mean K. In classical probability theory, we know that always can construct a certain probability space, namely omega bring as with Rn, and the sigma algebra is a product of sigma algebra, and the measure is the tensor product of that, and that marginal distribution. If you take a big probability space, and on this probability space, you take what's called a trajectory process, or some people call it coordinate process. The definition is bring each element in this Rn. Okay, you can see that a generic element of this you can view as a vector. Okay, and bring these vectors to the case coordinator. So that is really called coordinate process. Okay. This process and this family of random variable, this is a certain result one can study in the probability lecture, in lecture of probability theory, and what this sequence of random variables with respect to this probability measure, the distribution is just mu K. And also these random variables with respect to this measure, this probability measure P, and these random variables are independent, classical independent. Okay. And decomposition, I have shown you just as a picture to use interacting symmetric Fock space. One can do quantum decomposition. Okay. As a next step, we consider immediately this question. Instead of classical independence, now we ask other type of independence, a certain algebraic independence. Also, we ask, practically, we ask a question like this, to construct a Fock space. Okay. And another of that tensor product of many one-mode interacting Fock space, namely interacting the symmetric Fock space. As another of this, we construct a Fock space such that on this Fock space we can define for each K, we can define the creator, antilator, and if you consider non-general case, also define the preserving operator AK. Okay. And such that this Fock space creator, antilator, preserving operator are well defined for each K. And such that this property, with respect to the vacuum state, this sum, the sum of kappa operator, this vacuum distribution is just this mu k. I call this as a marginal property. And also, this sequence of operators, kappa operators, as k runs over in a certain cycle become a family, ask this family with respect to the vacuum state verify a certain algebraic independence. Okay. In particular about this independence, we consider effectively many algebraic independence. We consider these three, I don't know how to count 3 or 4, because this monotone and anti-monotone, one is very similar to another. In fact, we have all these 3. Okay. There are many other types of algebraic independence. So we focus ourselves in this case. Namely, to take this algebraic independence, we want to construct a certain Fock space. This Fock space for each K we can construct create, antilator, and preserve the operator, such that we verify this marginal property and this independence. Okay. This is the question from Mahat's position. Okay. I consider once again, in order to understand my idea, I added this assumption. All the mu probability matter are symmetric. In this case, Jacobi coefficient, only one family of Jacobi coefficient. Okay. This I have used this notation in the lecture of Jacobi. It's a probable infinity. It means probability matter is all finite movements. Okay. And since I have assumed the matter is symmetrical, so only one third of Jacobi coefficient. In order to take algebraic independence, of course we need algebraic probability space. In the lecture Cardiff has given the definition of algebraic probability space. Is a pair one is A, the star algebra, and this is a state. Okay, state is state. State means positively functional and also normalized. Okay. In my lecture, this star algebra is not necessary to have identity. It means it's not necessarily a unique algebra. In this case, what means normalized means, okay, in general case, this A, if this A is unique, then normalized means bring the identity operator to number one, as in the lecture of Cardiff show. I have said to see this algebraic independence, sometimes we must consider this star algebra is not unique. Means in this algebra there is no element so-called identity. In this case, what means the normalized means this state is a restriction of another state, and that another state is a state of this unique algebra. This is a direct sum of two star algebra. One is our star algebra. Another, this C is used as a star algebra. Okay, direct sum. This is a standard result of operator algebras. Okay, this for any star algebra, this direct sum is always a unique star algebra. Identity, what is identity? Just the pair, the first is 0, the second is 1. That is identity of this star algebra. Okay. In case of A is not unique, this free is normalized, means it's restriction of a state on this direct sum. Okay. At the first section, I want to see that I can see in my question to construct a certain box space. Okay. First of all, I show that this box space cannot be very simple. What I want to say. First of all, this box space cannot be symmetric box space. Means one must have some non-commutativity. You can consider symmetric box space or create anything person. As symmetric tensor product are commutative. Okay. If you want to do the quantum decomposition to realize also algebraic independence, you need no commutativity. Okay. To understand this, we see that the simple example, we see only we consider n equal to 2. It means we consider only 2 random variables. Okay. Number 1. In this number, I show you that if you start from algebraic probability space, then you consider A1, A2 sub-algebra of this A. Now you ask, with respect to this state, you ask Boolean independence of these two algebras. What means Boolean independence? Okay, I can here I can show you independence. Now we see this result. Okay, then if we ask also commutativity, then only very particular case can verify both Boolean independence and these two algebras are commutative. Namely, if you want to consider a general case, commutativity you cannot assume. Okay, if you consider commutativity of this type of independence, only very particular case can verify. Okay, this limit 1 means this result. Okay, let's see. We assume Boolean independence. I can show you later what means Boolean independence. It's one of independence, algebra independence, very easy to understand. Okay. And ask also commutativity between these two algebras. Okay. In this case, we assume Boolean independence commutativity, then these two cases must take. First possible case is the restriction of the state on one of these two algebras is true. That is zero, always zero. For some of index or restricts on one or restricts A2 must be true. Okay. Another possible case is for any k, for any element, two elements in this AK, and phi of a product is always equal to the product of phi. That means with respect to this state, any element in AK can be 1 and 2. Factorized. Okay. And as a sequence of this factorization, you can check easily this equality hold for all the n. And this equality practically means that with respect to the distribution of x is just a Dirac distribution. Okay. Let's say the independent definition of Boolean independence. Then we show that Boolean independence together with commutativity implies one of these three cases must take. Okay, so it means that in general you cannot assume commutativity. You must do that things in more commutative framework. Okay, this is some reference about that independence. Now we see this Boolean independence. I have seen this one of algebraic independence easily to understand the editor. Okay. Of course, you can find many difficult calculations, but as an idea, what means Boolean independence is very easy to understand. Okay, it means that we consider algebraic probability space a sequence of sub-algebra of this A. This is finally is Boolean independence, also the A, Y, 2, and so on are Boolean independence with respect to the state. You have to be simple. I wrote phi bi with respect to phi Boolean independence. Okay. And the definition is for any from 2 yards. Okay. For any this f in Fn, have defined Fn or somewhere I have defined. Okay. Where? Okay, I can explain what means this Fn. Here I define. Fn is such function, is a set of such function defined on set from 1 to n, bring the value in a set of natural numbers. Important feature of function in this class is this function calculated 2 consecutive points are different. It's important. So f1 different from f2, different from f3, and so on. But f1 could be equal to f3, for example. And for each such function in this Fn consecutive different recorder, for each element in the algebra with index f1 with index fn and so on, we take element x1, xn. Boolean independence means free calculate such product of x1 and xn are taken in this algebra factorize. Okay, this means these algebras with respect to the state free of Boolean independence. Okay. It's clear that if you consider only 2 algebras, one is index I, another is the index J. Okay, and these two algebra, if they are Boolean independence, and just this equality, just this equality formula 2, take n equal to 2. Okay, here x in one algebra, y in another algebra, so these xy belong to the different algebras and different sub-algebras, so the definition of Boolean independence gives the factorization. Okay. Because I formulate this because for giving proof of limit 1, I need only two sub-algebras. Okay. This is the definition 2 practically is a continuation of definition 1. Here what is a sequence of random variables, what means Boolean independence. Okay, now you can see the element in this star algebra. Each element in this star algebra we call as algebraic random variables. So now we have a family of algebraic. This family of algebraic random variables is Boolean independent. Currently, one say these random variables are Boolean independent. With respect to the state of free, if these sub-algebras AK, what is sub-algebra? AK, for each K, AK is star sub-algebras generated by xk. Practically, generic element in this algebra is a polynomial of xk and xk star. Okay, polynomial with two variables. One variable is xk, another variable is xk star. A generic element. Okay, mention that. Okay. And we see that this sequence of random variables are Boolean independence means this sequence terms of star algebras are more independent. Okay. Now you see, a proof is very easy, so I showed that there's not any difficult technical treatment. So I showed it's sufficient to do the trick ourselves we consider only two rubber variables. Okay, for each case, we take algebra variable in a case. Okay, such that xk equals 0. Otherwise, if it's sufficient to consider this case. Otherwise, what happens? Otherwise means there exists a case such that any element in that algebra, and this one always equals 0. In that case is exactly one of the possible cases like this. So it means that if this happens, okay, and then it's one of the possible cases. Then we consider if this is not happen, we prove that that one must happen. By this discussion, we consider the case. It is sufficient to consider such case for each case. In algebra, AK there's an element xk such that phi calculate xk different from 0. So we can just k. Now we consider k equal to 2. Okay. Now we consider phi equal to 2. Phi x2 in the second algebra, there is x2, phi x2 different from 0. Okay. We take two elements in A1. We see this product. Because thanks to the Boolean independence, this is in the first algebra, and this in second algebra, this in the first algebra. So and this in A1, in A2, in A3, index of this A are consecutively different. So we use definition of Boolean independence to do the factorization. Okay. Then we use the commutativity. We said two algebras are commutative. If commutative, we can exchange these two y and x2. Okay, we found this. Now this product of y and z, we view as one element in this algebra in1. We have fully calculated product of element in x2 and element in A1, element in A2. So once again we have this factorization. So we have this result. We have three x2 different from 0 in two parts. We can cancel this different from 0. What we have obtained is free calculate product of two elements. It's two elements in A1 can be factorized. Any two elements in this algebra A1 can be factorized. Then in discussion of induction, you can show that any product you write y and power n. Y is the element of A1, y power n is element of A1, like in this equality z. So you have this factorization. And discussion of induction, you continue this, you found this taken 3x2 different from 0, consider two elements y, z, and z in A1, I can extend, take 3xy as 0, y and z in A2. We get the same type of result, what type, such type of result. For any element in A1 or A2, we always have such equality. It's exactly what I have announced here. For each k, for any element in this AK, free calculate on the product can be factorized. And the discussion of by using this equality, the discussion of induction, we get this equality. So this shows that by assuming Boolean independence, assume commutativity, we have the one of these two case. So this result is practically suggests us to consider Boolean independence to assume no commutativity. Okay. Now I show you this remark. Here I have not formulated the result. What? I just show that this status, the same type of result, one can change, one can replace this independence, Boolean independence by other type of algebraic independence. After the commutativity, one gets the result by single, means only some very particular case. Okay, this remark. First of all, Boolean independence can be replaced by the monotone independence, equivalent to anti-monotone independence. This definition I will show you later. Okay. And we replace the Boolean independence in our assumptions and conclusions are the same. Okay. One can also replace the Boolean independence in one by full independence. But now you need assumptions. These two algebras, A1 and A2, share a common root. There's an element in the intersection of these two objects. It rules as identity. Means multiply from left, from right, is the same equal to that element itself. Okay. I just found that gave the idea of that result that remark. How many minutes I have? How many? I have almost 10 minutes. Okay, I can continue. Now let's see, to consider that algebraic independence, in particular, Boolean independence and monotone independence, similar anti-monotone independence. Also, we have a discussion of identity. For free independence, we can assume an existence of identity also without identity. But from Boolean independence and monotone independence, discussion of identity are very important. Okay, now let's see this.
Hello?
This is
Hello?
this improvement will still algebraic probability space to some algebras. Okay. If we can
Hello, Professor Ezekiel.
I will give proof on only for probabilities. Up now, I have not given definition of non-independence. Okay. I show you, I wrote the result here. I show that I explained the proof. Okay. And I will consider the rule independence. Okay. And easily verify its independence, easily share the common identity. Then for any k equal to 1
use the microphone
and always have these properties.
Hello, Professor Lu. Yes, you have spent 1 hour. So I can round up in 5 minutes.
Yes, sir.
Okay.
Yeah.
So in 5 minutes, round up so that we can go.
I must stop here.
Yes, in 5 minutes you can round up. You have spent 1 hour.
5 minutes. Okay. You see, also in this case, you see that identity very influence in the case of the Boolean independence and the non-independence. If you consider two algorithms, Boolean independence or non-independence, if you assume that we have a common identity, only these children, only. Okay. So this means that if you want to consider Boolean independence or non-independence, in general picture of this, you must consider general picture in which any two subalgebras has no common identity. Okay. Alright, you have this short case. Now, I show you. Okay, the proof is very easy. If we have common identity, it means that the elements of the identity, multiplication does not change anything. Okay. Then we see this free coverage product. And since this is identity, so we can add identity product within the C. Now, these two elements, x1 and y, we take in A1. And A1 and A2 are common base, means this identity I can view as element of A2. And so we can free calculate the product. This element in A1, this element in A2, this element in A1, so independent primitively to factorize. In fact, here one must add free calculate on the identity, free calculate identity of 1, so we get this point. Once again, you get this factorization, means we have proved this point. If we have full independence, if these two subalgebras share a common identity, then must happen this means we have a rather trivial case. Okay, so this suggests us to consider Boolean independence or non-independence in case of without common identity. Okay, I can stop my lecture here. Okay, thank you very much.
Yeah.
Questions?
Please let's give Prof a round of applause. So thank you, Prof, for the lectures. Please, I hope you can hear me. Can you hear me?
That's
Please unmute. Have you observed me? On mute. Can you hear me, Prof?
Yes.
Dr. Lu?
No.
Hello, Professor Lu, can you hear me?
He has already muted.
You have been muted.
That issue unmute him.
Okay. Please unmute Professor Lu. Unmute.
He's already muted.
Can you hear me? Unmute. Oh, thanks. So, yeah, we appreciate your lecture, and we want to ask for questions. Those online, if you have a question, please you can raise your hand. And those in the class here, please let's identify for questions on the lecture Professor Ayoola. Anyone? Okay, online. Okay, I have a question. I have a question. Can you hear me?
Clearly.
Okay, good. Now, the description you have given now, I can remember yesterday that we were made to know that this description applies for yesterday to the federal case. I want to know, is this the same now too? Because using the Boolean and the commutative operations that you have described, does it also apply, to the federal case? And I have not seen the operators that we have been describing, maybe the annihilation creation as described by Professor Agadi in the probabilistic algebraic conversation. Can you get my question? Can you hear me?